Hello and welcome back. Okay, this is the second in our series on distributions, which is going to provide you the foundation of how all quantitative analysis, how all statistics works. Okay, so we talked about the normal distribution. This time we're going to talk about sampling distributions, and it gets a little bit freaky. Um, so let's see. So some definitions. Sampling error is the variability of a statistics from sample to sample due to chance. Okay. For example, if you calculated the mean of a random sample of 100 SAT scores from 2015, then you calculated the mean of another random sample of scores from the same year, the two means would be different even though the samples came from the same population. Okay, they would be different, and the means would probably be different from the overall population mean. And the difference between the overall population mean and the means of the samples is sampling error. Sampling distribution is the distribution of sample statistics that we would see if we repeatedly drew multiple samples from one population. I'm going to show you a demonstration of this. For example, if you kept taking random samples of SAT scores and calculated the mean for each one, then you graph the means of the samples, you'd be looking at the sample distribution. So we're used to, if this makes no sense, don't worry. It will make more sense by the end of this lesson. Okay? Um, we're used to thinking in terms of scores, right? We have a collection of scores. We get an average or mean of those scores. Those scores, we can plot how many kids got each score, and we see what the distribution is. Okay? We're going to take it a step further in this lesson. So, globally, in 2015, about 1.7 million students took the SAT. The mean score of the population, mu, right, was 1490 out of 2400 in that year. The numbers are higher than back when I took my SAT. But anyway, the mu was 1490. However, for the typical research project in education, we almost never know the population mean and standard deviation. Okay? Therefore, we can't use z-scores to estimate how probable a particular value is. We almost never know. Okay, we're collecting our own data, we're using our own tests. We're using a test that isn't as widespread as the SAT, and we may not be able to find a population mean and standard deviation. The special properties, however, of sampling distributions make it possible for us to make inferences about the population. Okay, there's some special properties that allow us to make inferences. Let's find out more. Okay, so population of students, that's this big group at the top, and the samples are the little groups, right? The little bubbles coming out of the big bubble. All right. So, course ratings. Let's talk about course. Here's an example. Course ratings, right? If students are asked to rate this course on a scale of 1 being terrible to 5 being awesome, um, imagine that, okay? Each time the course was given, there might be a different M or X bar, right? A different average rating for that class. And that class is a sample, constitutes a sample, right? Because it's a part of the population. What if we made a histogram with each class's average rating? It would show the distribution not of ratings, but of average ratings. Okay, we're not showing the distribution of how each student scored the this course, but the average ratings for each class that took this course. You see that? A little different, right? So we're no longer looking at the distribution of scores. We're looking at the distribution of mean scores, the distributions of a statistic from a sample rather than a number from an individual. You see? Okay, Let's keep going. There's a simulation that you can look at to explore this. And if you click on that link, it'll take it to you. It's really cool. I definitely recommend trying it. And I'm going to show you an example of what happened when I did that simulation. Let's talk about another example. We talked about course ratings. Now let's talk about the length of newborn babies. The population mean length of newborn babies is 20 inches. Let's imagine that this population standard deviation is about 3.5 inches. It's actually more like 1 inch. So normally, you get the announcement and the baby was either 19 inches or 20 inches or 21 inches, probably not much beyond that. The graph shows the distribution of the birth lengths of newborns if the standard deviation was 3.5. It's not. With one, it made too skinny a distribution. I was like, that's going to be hard to talk about. Let me spread this out a little bit. Okay, so this is the population, right? These are the lengths. We're taking these actual babies, how long they are at birth, right? So the length of babies. Now, what if we take samples? Okay. If we randomly look up the birth records of 5 babies, right? Average their length and graph the mean length of those 5. Okay. And so we had one sample, that sample on the simulation it like drops down. And we see what their average is. We're graphing their average, okay? And this is the frequency. So we on the y-axis is the frequency. On the x-axis is the average length of these samples, right? So we took randomly 5 babies, and then we do the same thing for another 5, and the same thing for another 5, and the same thing 5 times, okay? And we would get the graph on the top if we drew 5 samples. Okay? If we randomly look up the birth records of 20 babies, average their length, and graph the mean length of those 20, then do the same thing for another 20, and so on 5 times, we get the graph on the bottom. Okay? And I asked the question, what is the mean for the top distribution of means? How about for the bottom? What is the standard deviation for the top? How about for the bottom? Let's see. And in blue, we have a mean of 20.47, and in red, a standard deviation of 1.56 for the top graph. For the bottom graph, we get a mean of 20.18, and so in our population, we know the mean was 20. So these means are all close. The means of our graphs of means of samples, okay, are very close to 20. Standard deviation of 0.9. So our standard deviation for our population was 3.5 inches. And for each of our examples here, our standard deviation is smaller than that. Let's keep going. Now, so we did it 5 times before. Let's say we do it 10 times, okay, where we're drawing these samples. If we randomly look up the birth records of 5 babies, average their length, and graph the mean length of those 5, and then do the same thing for a total of 10 times, we get the graph on the top. If we randomly look up the birth records of 20 babies, average their length, and graph the mean length of those, it should say 20, then we do the same thing for another 20, and so on for a total of 10 times this time, we get the graph on the bottom. What's the mean for the top distribution of means? How about for the bottom? What's the standard deviation for the top? How about for the bottom? Let's look at that. The mean in blue on top for when we're drawing 5 birth records at a time is 20.23, very close to 20. The standard deviation, 1.2 inches. Okay? So still smaller than 3.5, which is what it was for the population. The mean on the bottom, we got 19.86. Again, very close to 20. Standard deviation, 0.78. Really small, less than 1 inch. Standard deviation. And look at the shape. Look at the shape. Hmm. Oh, look at the shape. Look at the shape. Look how the shape is changing. Okay. If we randomly look up the birth records for five babies, average their length, and graph the mean length of those five, then we do the same thing for another five babies, and so on 200,000 times. We get the graph on the top. And what's the shape of that graph? If you said it's a normal distribution, you are right. Yes, symmetric, mound shaped. Okay, it's a little peaky. That's called kurtosis. It's a little peaky, little pointy at the top, but basically symmetric, mound shaped. Okay, let's do the same thing with 20 birth records at a time. Okay, we randomly look up the birth records of 20 babies, average their length, graph the mean length of those, you should say 20. Then we do the same thing for another 20 babies, and so on for 200,000 times. We get the graph on the bottom. Okay, now that's very peaky, huh? You see how pointy it is at the top? Okay. But basically, it's symmetric, right? And it's like a very skinny Bell distribution or normal distribution. Look at these means and these standard deviations. Okay, so the mean of the top graph, mean of 20.01. We're getting really close to 20 here, y'all. The standard deviation, 1.55. We're still far away from 3.5 inches for the standard deviation. On the bottom, again, mean of 20.01, very close to 20. Standard deviation of 0.78. Okay, smaller standard deviation, and and we're far away. 3/4 of an inch is far away from 3.5 inches. Okay, so you get the picture, right? To create a sampling distribution, we made a histogram of the mean values of a bunch of samples drawn from the population. If we kept drawing more and more samples, the sampling distribution would get closer and closer to being a continuous normal distribution. Okay? So we're seeing that it's a distribution of averages, not a distribution of lengths, distribution of average lengths from a whole bunch of different samples, the sampling distribution. When each sample has more members in it, remember sometimes we were drawing five birth records, sometimes we were drawing 20. When each sample has more members in it, the normal distribution has a smaller standard deviation. Okay? When it has few members in it, it has a larger standard deviation. Also, by the way, the standard deviation of a sampling distribution is called a standard error. It just has a different name. The standard error is always smaller than the standard deviation of the original population. So the standard deviation of the original population was 3.5 inches, and we kept seeing these like 1.5 inch, 1 inch, less than 1 inch for the standard deviation of our samples, our sample means, right? So we have a bigger standard deviation for our population distribution than for our sampling distribution. And the more individual records there are in each of our samples, the smaller the standard deviation or standard error in that case. Isn't it kind of freaky? We can summarize all of these properties um, um, in the central limit theorem. So yeah, we didn't actually discover this by doing the simulation in this class. We didn't discover these properties. Someone else had already discovered them. Um, the central limit theorem. Okay, so here are the properties of that theorem. As samples get large, greater than 30, the sampling distribution has a normal distribution with a mean equal to the population mean. Okay? as samples. When you draw a sample greater than 30, we got like a normal distribution with only drawing 5 or 20. But we were able to do it 200,000 times in a simulation. In the real world, if you have more than 30 in your sample, the distribution of means, if you were to repeatedly draw samples of 30 or more, the distribution of means would have a normal distribution with a mean equal to the population mean. Okay, so we could figure out what the center is, and then that'll let us know we've taken samples. We haven't sampled the whole population, um, but it'll let us know what the population mean is. Okay, and the standard error or standard deviation of the sampling distribution, the standard error can be calculated using this equation, okay, where sigma equals s divided by the square root of n, okay? Sigma, the standard standard error, equals the standard deviation divided by the square root of n, the standard deviation of our sample, divided by the square root of the number of data points in our sample. This is key. If we know the center and we know the typical distance from that center, we can tell if a mean is typical or unusual. And thank you, Demoivre and Laplace, for um, uh, describing and publishing and exploring and proving the central limit theorem or some aspect of it. So that's it. That's it. Sampling distributions. They let us know the center and the typical distance from the center that a mean would have. Okay? Um, yeah. And we'll find out more about why that's important in the next lesson. Okay. See you later.